Let's do a couple of real easy reminders here. Well, let's do the full thing here. Find that derivative. That'll get us just a little start. All right, we can skip over this transcendental stuff. Transcendental functions as opposed to algebra functions. Like all the weird functions are transcendental functions. Now there's a more technical definition, but we don't need to worry about it. Let's do a little bit of algebra review because calculus is easy, algebra is hard. So we're gonna do a little bit of algebra review to make sure we're okay before we get to the calculus. So xy to the m, that would be the same as x to the m, y to the m. Right? If you're, I don't even like to say PEMDAS because that is misleading, but you can distribute exponents to multiplication, and you can distribute multiplication to addition. But you can't distribute exponents to addition. That's a little separate. That's not allowed. What do we do when we are multiplying with the same base? You know what? Let's back up. Let's do something that I know you know the answer to. What's x squared times x to the fifth? X to the seventh. So what did you do with the 2 and the 5? You added them, so x to the m plus n. Sometimes it's easier with actual numbers than with letters. The next one is the power and root thing. Right? The power grows on top and the root grows underneath. Flower power. We've used that a lot already because we can't take a derivative of a root, so we have to use that rule. How about power to a power? Like x squared to the fifth. What would that be equal to? X to the 10th, because you multiplied. X to the 0. What's x to the 0 equal? 1. And x to the negative 1? 1 over x. Pretty easy stuff right there. It's a little bit of a side note. None of those are exponential functions. An exponential function has to have the variable in the exponent. Like y equals e to the x. But there's still properties that we can apply and use. Right, let's graph y equals e to the x, which you graphed in pre-cal, but perhaps a refresher. So let's put in 0. Dylan, what's e to the 0? Yep. So 0, 1 is on my graph. Let's plug in 1. E to the 1 would just be e, but what's e equal to? 2.7 something, yep. So there's a point at 2.7-ish. Let's get one on the other side. This one is a little bit weird. Maybe. E to the negative 1. What's that equal to? 1/3 is where I'm headed, yes. It's equal to 1 over e, which is sort of 1 over 2.7, which is sort of 1/3. That's a lot of sortas, but when it comes to the graph, it's close enough. So negative 1 comma 1 over e, or 1/3. So there's our graph of y equals e to the x. Now, with the picture, limit problems are supposed to be easy, so that means I can pick on some people like Bella and Austin. So Bella, as x goes towards negative infinity, so as x heads out this way, what's our graph doing? What is e to the x doing as x goes out this way, further and further? What's it approaching? Is it headed towards something? Is the y value headed towards something? 0. Okay, so the function doesn't get to 0, but the limit is 0, because the limit means what are we getting close to. Austin, on the other end, as x gets bigger and bigger, what is the y value doing? Good. Infinity. And doing so rather quickly. Right? Like natural log was just like creeping up toward infinity. E to the x is like exponentially heading toward infinity. Y equals e to the x has a horizontal asymptote. Braden, do you think you could identify that horizontal asymptote for us?
Y equals 0.
Y equals 0. With confidence. From the graph, or from the equation, or from a table, e to the x is never negative. Because if you plug in a negative, you don't get a negative value, and the negative flips it over. So e to the x is always positive. One more graph. Natural log and e to the x are inverses of each other. That's why we use them when we're solving for the other. So I'm going to go ahead and graph natural log of x. Maybe seeing both of them will remember both of them. All right, so that idea that they're both headed toward infinity, but e to the x is getting there a lot faster than natural log is. All right, we're going to skip over the derive, discover stuff because it takes too long. Let's jump to the box here, the important box with our answers in it. So the derivative of e to the x, here's the big thing for today. The derivative of e to the x is e to the x. It's the only function that's like that, where it is its own derivative. Now, if you don't just have an x in there, if you got some other thing up there, so the rule still applies, it's e to the u, but then you need the chain rule, so the derivative of the exponents. But either way, you're not changing the exponent, you're just tagging on for the chain rule. Right? If the base is not e, right? We went from e, which is a number we like, to a, which is just some other number not named e. Do you remember what we had to do when the derivative of a log wasn't base e? Yes. 1 over natural log 8, and then the rest of the problem 1 over x. Okay, it's similar here, but logs and exponents are inverses. So instead of dividing by natural log of 8, we're going to multiply by natural log of whatever the base is, so natural log of a. But then the rest of the rule is the same, a to the x. And then sort of the most complicated form, the base isn't e, we need a natural log a times a to the u times u prime. Again, the u prime is just the chain rule part. So most of our problems are not like the top left piece, because that's just not much going on there. Most of our problems are this version. So with e, but when the exponent is not just x. And then we can get goofy and put in some different bases. Do these real quick, because this is what will confuse people. Probably not today, but later on when you first see one of these, after you haven't seen them in a while, work those two problems to see the difference between them. Alright, let's do some examples. Find the instantaneous rate of change. Again, we like just using all the different words to make sure you remember that that really just means the derivative of y equals e to the 4x cubed when x is 1/2. So dy dx equals, all right, I like the base of e, so I don't need like that natural log of anything in there. So e to the 4x cubed times, chain rule, 12x squared. Why doesn't that look like any of my answer choices? Yeah, I got to plug in 1/2. So e to the 4 times 1/8 times 12 times 1/4. So let's see, 12/4 would be 3, and 4/8 would be 1/2. So 3 e to the 1/2. Again, the new rule today is easy. It's just all the stuff before it and after it. Problem 2 should go relatively quick. The derivative of e to the x is e to the x. What about the derivative of e to the 2x? E to the 2x times 2, and then I'm going to put the 2 in front just because it looks a little better. All right, you do the next 4. Zoom for the video. There's the answers to A through F. Fast forward a little bit. JT, why is Braden telling you to put a 2 in front of it? He's right. Where does that 2 come from? Okay. Exponent's an okay answer. Chain rule is what we're really looking for there. Keep the e to the 2x the same, and then chain rule off the exponent. Isabella, what's the derivative of e to the 2x plus 1? It is the same thing, right? Because the plus 1 minus 1 doesn't matter when it comes to a derivative, because both of those parts are 0. Okay, quotient rule. GF prime minus FG prime. So GF prime. So I need to tie those two together first. So 2e to the 2x, e to the 2x plus 1. Now, I know I said GF prime and then I wrote F prime G, but they're multiplying, so I can put those in a different order. Minus the other way around, FG prime, 2e to the 2x, e to the 2x minus 1. All over the bottom squared, but I'm not, like, I look at my answer choices and they all have that, so I'm not worried about that. Now it's an algebra problem for the top to see what it simplifies to. So 2e to the 2x times e to the 2x would be 2e to the 4x, because we added the 2x and 2x and got 4x. Plus 2e to the 2x minus 2e to the 4x plus 2e to the 2x. Let's see, the e to the 4x's will cancel, and that leaves me with 4e to the 2x over the denominator squared. 4e to the 2x over the denominator squared is answer choice A. Calculus is easy, algebra is hard. Would not be negative. This negative sign helped this one cancel, and then negative times negative made that one positive. What rule for number 4? Product rule. So let's skip that one. Let's do number 5. What's different about number 5 that would make me want to make sure we see number 5? Yeah, that base is a 3 rather than an E. So that means there's just an extra natural log 3 as part of my answer. The rest of it's the same. So 3 to the 4x squared times the derivative of 4x squared worksheet X. I don't know that there's any cleanup you could do on that. Looking at my answer choices, it's not in the bottom. It's in a different order, but answer choice A. Let's skip down and quickly do number 7. H equals E to the F times G. So putting multiple rules together here. So I got E to something. So the derivative of E to something is E to the thing. So E to the F times G. I'm going to leave off the parentheses and X's because that just muddies things up. But I'm not done. I have to chain rule. So now I need the derivative of F times G. So F prime G plus G prime F. And then I want to evaluate all of those at 6. So I need F of 6 and G of 6 and F prime of 6 and G of 6 and so on. How am I going to get F prime at 6? Okay, what am I looking at on the graph? The slope. So we're out of time, but I wanted to get to that because it was one of those equations with exponents and chain rule and graphs and lots of stuff going on. Alright, we're on to worksheet 3. This will be due on Friday with a quiz up through this stuff and including this stuff.